All right, we're back with example 2, but before we get started, we need to go over some theorems. So the first one is 341 theorem. It states if two intersecting lines form a linear pair of congruent angles. So if two intersecting lines form a linear pair of congruent angles. So let's look at what that would look like. So here we have two intersecting lines and they form a linear pair. These two angles are a linear pair, right? They form a straight line and they're congruent. We can tell by those arc marks. Then the lines are perpendicular, okay? And so what we can say is that they're perpendicular, and there's a misprint here. So let's go ahead and make this a L would be perpendicular, right? This section is all about perpendicular lines. So we're going to learn 3 theorems that have to do with perpendicular lines. So if you have two intersecting lines that are a linear pair and both of these angles are congruent, then what you know is L is perpendicular to M. And then this is the reason. So if you're on a proof, this is the reason. Two intersecting lines form a linear pair of congruent angles, therefore the lines are perpendicular. So you just have to write all that. Okay, the next one is 342, perpendicular transversal theorem. And this theorem has a name. That's the name. And it says in a plane, if a transversal, okay, is perpendicular to one of two parallel lines. Okay, so we have two parallel lines here. We have a transversal, and the transversal is perpendicular to this line, then it is perpendicular to the other line. And that makes sense. So we know that Q is perpendicular to P, right? And it makes sense, right? Because whenever we have parallel lines, we can use those 4 theorems. We can use corresponding angles postulate, alternate interior angles theorem, alternate exterior angles theorem, and same side. And really, if we know that these two lines are parallel and we know that this is 90 degrees, we know that that corresponding angle is also 90 degrees, which means that P and Q are perpendicular. So that is the perpendicular transversals theorem. Okay, and I want to say before we go any further that all of these need to go on a flashcard. Okay, whoa, flashcard. Okay, so make sure we're going to go over 3. This is theorem number 1, theorem number 2, and now we're going to talk about theorem number 3. Okay, theorem number 3, 343 theorem. It states if two coplanar lines are perpendicular to the same line, okay, then, so we have a transversal, we have two lines, and they're perpendicular to the same line, then the two lines are parallel to each other. So R is parallel to S. Now, does that make sense? So if this is 90 degrees and this is 90 degrees, I mean, we just went over all that converse stuff, right? And they're corresponding angles. So 90 and 90, they're the same. Then by really the converse of the corresponding angles postulate, we know that R and S are parallel to each other. So this is the 343 theorem. Two lines perpendicular to the same line. If two lines are perpendicular to the same line, then the two lines are parallel. And this is the reason for that right there. Okay, let's look at a couple examples and see how this all plays out. Now, know that when we just talked about 1, 2, 3 theorems, right? This one, what was this one? This was if you have two intersecting lines and they're a linear pair and they're congruent, therefore L is perpendicular to M. We talked about the perpendicular transversal theorem, which basically says if you have parallel lines and one of the lines is perpendicular, so to the transversal, that means that the transversal is also perpendicular to P. So we can say Q is perpendicular to P, right? And then this last one, if we have two coplanar lines are perpendicular to the same line, then we know that those two lines are parallel. Okay, so just having some math street smarts, we just talked about 1, 2, 3 theorems that have to deal with perpendicular lines. So when we go ahead and we start working on these examples, you know that these examples at some point are going to have to do with one of these, or their applications of these particular theorems that we just discussed. So as we look at these problems, you want to think, okay, does it have to do with the first one? Does it have to do with the second one? Or does it have to do with the third one? Because at some point, each of these examples is going to use one of these theorems. All right? So let's look at this first example with that in mind, okay? It says, write a 2-column proof given that R is parallel to S and angle 1 and angle 2 are congruent. What we need to prove is that R is perpendicular to T, okay? R is perpendicular to this transversal here. Okay. So let's look at everything what we have. We know at some point we're going to use this, but we also are going to use everything that we've learned so far. So we just have to figure out, well, which of all the things we learned before are we going to use for this example? So, okay, the first thing it gives us is R is parallel to S, okay? So you should immediately think of some things when you see that R is parallel to S, okay? What are you thinking of? You should think about something. There's 4 things that should instantly come into your mind when you see R is parallel to S. What are they? Yes, you were right. The corresponding angles postulate, the alternate interior angles theorem, alternate exterior angles theorem, and the same side interior angles theorem. Okay, so you know that when you have these 2 lines are parallel and there's a transversal, you can use any of those 4, right? So what do you think you would use for this one? What I see is that 2 and 3 are corresponding angles, right? So since these lines are parallel by the corresponding angles postulate, you know that these 2 angles are congruent. So we know that angle 2 is congruent. And I'm just using the color, the green color, just to show that those 2 angles are congruent to each other. Okay. All right, perfect. Then what do they tell us? They tell us 1 is congruent to 2. So if 2 is green, that means that 1 is also green. Okay? So remember, what are we trying to do? We're trying to prove that R is perpendicular to T. So what do we see? We see that we have 1 and 3, which are both green, which means they're both congruent. So which of these theorems are we going to use? Which is the one that unlocks the door to be able to show, to prove that R is perpendicular to T? Is it theorem number 1, theorem number 2, theorem number 3? What do we have? We have that 2 of these angles that are right next to each other are congruent. What do you think? Okay, if you said the theorem number 1, you would be correct because it says 2 intersecting lines form a linear pair of congruent angles, then the lines are perpendicular. And that's exactly what we have. We have a linear pair here of congruent angles, so therefore we know R is perpendicular to T. So that's pretty much the groundwork for what we're going to write for this proof. So let's just go ahead and write it. So the first thing we're going to do is just write all of that given information. Well, I'll just write the RS. Okay, so that's given, right? And then this is like the key that unlocks the door to knowing that 2 and 3 are congruent. So angle 2 is congruent to angle 3 by the corresponding angles postulate. All right, then we can kind of throw in that other piece of given information. Angle 1 is congruent to angle 2. That's given. And then you can see that in this statement, do you see it? They're both, angle 2 is here and angle 2 is here. So angle 3 is congruent to angle 2 and angle 1 is congruent to angle 2. So how can we say, so since these angles are congruent to the same angle, we know that they're congruent to each other. Do you remember what that reason is? We can state that angle 1 is congruent to angle 3. Do you remember? Okay, if you said the transitive property of congruence, you would be correct. Okay, and then we have angle 1 are congruent, so we can basically say that R is, I'm going to change this to a lowercase t because it's a lowercase t, is congruent to T because of the, we just say it right here, the two intersecting lines form a linear pair of congruent angles, then the lines are perpendicular. So that's the reason. I'm going to put a 5 here. So two intersecting lines form a linear pair of, I'll say it down here, congruent angles, then the lines are perpendicular. All right, perfect. Okay, so let's go ahead and look at this second example here. All right, so check it out, example 2. Look at all this information we have. So it says, given angle EHF, so EHF is congruent to HFG, so this angle, so those two angles are congruent. Then the other thing it tells us is that FG is perpendicular to GH. Okay, what we need to prove is that EH, this line here, is perpendicular to GH. All right, there's a lot going on. This picture looks pretty complicated. So let's just try to take this piece by piece. So the first thing I'm going to look at is this EHF is congruent to HFG. EHF is congruent to HFG. Okay, so we know that that's, and sometimes when I have like more complicated pictures like this, I just want to try to make it simple. And so the way that I'm going to make this picture a little bit simpler is just by taking this line and just kind of extending it here, and then taking this line and extending it here, and then taking this line and extending it right here. And if you can start to see, I really have something that looks like that, okay? Which is exactly what we've been dealing with, right? With two lines and a transversal. So that's what we have here, except what they're stating here is that these two angles are congruent. Okay, which would be the ones right here and right there. And so if we think about this as two lines and this is our transversal, these are, we want to think about why are they giving us these angles here? And we want to know, okay, they're saying that they're congruent, so what type of angles are these? And if this is our transversal and we have two lines, these are alternate interior angles, right? And they're saying that they're congruent. So what do we know? We know that we have two angles, alternate interior angles that are congruent. Therefore, by the converse of the alternate interior angles theorem, we can state that these two lines are parallel to each other. All right, and that's kind of huge, okay? So it's kind of like dominoes. They give you one thing and you press it and it goes boom, 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 boom. So the fact that they give us these two angles here is for the purpose of knowing that you can use the converse of the alternate interior angles to prove that these two lines are parallel to each other. So let's just go ahead and start there. So I'm going to write that down. What did we start with? We started here. So angle EHF is congruent to angle HFG, right? That's given. And because of that, we can state that these two lines are parallel. So line EH is parallel to line FG by the converse of the corresponding angles postulate. All right? So now the question becomes, why did they give us this information to show that these two, I'm going to use red to show that, okay, these are parallel, right? So these two lines are parallel. Okay, so we have that the lines are parallel, and then the other piece of given information is that FG is perpendicular to GH. So we know that these two lines are parallel, and we know that FG is perpendicular to GH, and we are supposed to prove EH is perpendicular to GH. Do you guys have any ideas of how we might do that? So this is always when I like to go back to what we were talking about, okay? Do we have a situation here where we have a linear pair of congruent angles? I would say we do not. Do we have a situation here in a plane if a transversal is perpendicular to one of two parallel lines? So, okay, if a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other line by the perpendicular transversals theorem. I think that's what we have, right? Because we proved that these two lines are parallel, right? And then FG is perpendicular, and this is the transversal HG. So because it's perpendicular to this, HG is perpendicular to this parallel line, it also HG must be perpendicular to this line as well by the perpendicular transversals theorem. So boom, there we have it. So we're just going to go ahead and write down this given information here. FG is perpendicular to GH. Line FG is perpendicular to line GH. And because FG is perpendicular to GH and these two lines are parallel, which we just stated there, we can state it, we can prove it that EH, line EH, is perpendicular to GH by the perpendicular transversals theorem. Oh, perpendicular transversal theorem. I think I got so excited I forgot to write that this information is given. So yeah, there you have it for example 2. So yeah, make sure that all of your notes look the same as mine do, and I will see you in a little bit for example 3.